its properties. The last time we looked at the existence of a derivative operator by simply using finding an operator on a specific coordinate basis. We can define it that way and then transform it, does it using the tensor transformations to any other coordinate basis, but it didn't keep the property that the components in the new coordinate basis would actually be the partial derivatives of the components on that particular basis. So that property was lost. But we did show that we could at least find something that satisfies all our axioms or requirements for derivative operator, but it didn't satisfy our intuitive understanding of what a derivative operator meant. And then we went on and we started looking at uniqueness. So, and that's what we're going to do today. And everything we've done up till now in defining the derivative operator hasn't assumed a metric. So even though we introduced the idea of a metric that maps our dual space or identifies our dual space with our vector space at a point, we said wait with that thing. We'll see what role it plays later on. Let's do the derivative operator and that idea of parallel transporting vectors in the most general way possible. Okay, and so I'll just start with a reminder of the 5 axioms, like condensed quickly, of what the derivative operator is before we start going on. Okay, so just from last lecture we have our derivative operator. It works on a tensor and our abstract index notation. It is linear. In other words, it basically has this property if you express in components, and we're going to use this in some of the proofs that follows, which is why I'm reminding you. It's basically the product Leibniz's rule, or the product rule that allows you to take the derivative of the exterior product of 2 tensors. It's simply the derivative applied to the one times the other plus the derivative applied to the other times the first one. Okay. 3, we had the idea that taking derivative operator commutes with contraction. In other words, it doesn't matter in the order whether you contract the thing first and then take the derivative, or whether you first take the derivative and then contract the thing. They are assumed to be equivalent, and this is actually a property we're going to use repeatedly today. So just the way it's written out is kind of important. The last 2 had to do with functions, applying the derivative operator on functions, and we basically used that to, in some sense, peg the operator to something we know. So we basically said that the derivative operator applied to a function can be used to express basically that this expression holds, that if you have an element of your vector space, which is basically a function from the space of all functions on the manifold to the reals, you can express it this way. It's basically the abstract components contracted with the gradient or the derivative operator applied to the function itself. And this is very, very useful because it's basically the only tangible thing at the moment, one of the only tangible things at the moment that we know about the derivative operator. It's basically that it reproduces our idea of a directional derivative and a tangent when applied to functions on the manifold. Okay, and then we had the second one that's also related. It basically had this commutative property, basically that the order of derivative operators applied to a function doesn't matter, it's reversible. And this is only true for a function. If it's applied to a function, it is not, we're not requiring it to be true more generally if we apply it to tensors. Okay, it was true, however, that when we constructed our coordinate derivative operator, that it held for all tensors if we'd constructed it in that way. But that is something a requirement we don't make, and the reason we don't make it is that it's actually not possible to do that on a curved manifold and maintain our intuitive identification of derivative operators with taking derivatives in a coordinate invariant way. Okay, but this one is useful, and we're going to use it again in our derivations. Okay, and then we went on, and I just want to get the result again. We started asking the question of the uniqueness. So suppose we know at least one derivative operator exists. The one we found doesn't behave exactly as we wanted to do, but it does exist, it satisfies all those axioms. And then we started asking the question, suppose we have a manifold and we have more than one derivative operator on a manifold, what is the relationship between the two? Okay? And the first observation that we made is, well, we can use 4 and 5, and if we apply it to a scalar, the thing is the same, right? So by 4, if we're applying both derivative operators by this identification with a directional derivative, the two operators applied to a scalar will give exactly the same result. And then we went on and we looked to investigate what happens if we apply it to basically a covector, a one form. And we derived our first identity, namely that if we rescale that covector and we still apply the derivative operator, it's simply the function times the difference between the derivative operators being applied. Okay, so that identity we derived last time. What I'm now going to do is I'm going to work out the consequences of that identity. Okay, when I initially learned this thing, they weren't obvious, but the consequences are profound because everything rests handles on it. And once you've heard it, it looks obvious and it looks as almost if you said nothing. But it gives a very powerful way of actually eventually going all the way to computing how you do work with a derivative operator. So that particular equation implies, and I'll put this as a proposition, that the derivative operator applied to a particular one form depends only on the one form at P. Okay? And the reason why this is important, our intuitive idea of a derivative operator is that it sort of keeps track of the gradient, how you're moving off of a particular point. And now that statement that the difference between two derivative operators is only dependent of the value at P basically seems a little bit counterintuitive. But it needn't be, because if you observe, it's the difference we're taking. So in some sense, if we apply the coordinate derivative operator, the moving off of that particular point P is encapsulated in that part. Okay, and this statement actually makes that concrete. So when we start studying the difference between two potential derivative operators, and we say that they only depend on the value at P, that doesn't negate the statement that a derivative operator in general, it doesn't say make that statement true for a derivative operator in general, but it's important that it's a difference. Okay. So, and I mean, before I go on, the way I think about it is that you have these two parts, just as I mentioned the last time. If you take a derivative of a point, you have the one part that actually takes the account of how the components are changing from one point to the next, which is captured in like the real derivative, the derivative operator that we defined, the coordinate derivative operator we defined with respect to the components. But you have a second part that keeps track of how the actual vectors, the underlying basis vectors are changing. And this is what's being captured in this thing. Okay. So the proposition is this one, and we want to prove it. And the way we prove it is, suppose we have another cotangent vector field, right? So this is important. So cotangent vector field, and the cotangent vector field agrees with the original one. So the prime field is the new one, agrees with the original vector field only at a specific point. Okay, so you can imagine two smooth covector fields, and only at point P they have one vector in common. And what you can then do is replace omega by omega prime in the above expression, or in that expression. And if it makes no difference, then you basically proved that it only depends on the value at P. Okay, so what we're going to do is we're simply going to go through and actually do that. So you're assuming you have two different vector fields, covector fields that agree at P, and this identity basically holds for both of them. Okay, if you replace the one by the other and get the same answer, you've proven the proposition. So that's just what I'm going to do. Okay, and the crux comes by saying you can expand or you can express the difference between the two covector fields in general. Or in general, if you have two vector fields that agree at P, you can express their difference in the following way. Okay, and now be careful. We haven't chosen a particular basis here. We're still using our abstract index notation. But we are making an expansion in terms of other covectors. Okay, it's basically, we can express this difference as, like in other covectors, times by functions that vanish at the point P. So these functions enforce the fact the things are exactly identical. They're n of them, so you can always expand any covector on a random basis, which you have not defined, and which is, or a random basis of covectors, and you can always find functions that multiply them in front, that is 0 at the thing. This is very, very similar to the way we actually constructed the coordinate basis. Remember when we, on the actual manifold, we simply expanded it, except that I'm still keeping it abstract this way. And you can always do it. There's nothing dodgy about doing this. The main feature is that these functions vanish and at the point P, enforcing that the thing is exactly the same. Okay, so if you do that, if alpha are smooth functions that vanish at P, and mu beta alpha are smooth vector fields, it doesn't really matter what they are, it's just this is a rigorous expansion. Then we're now going to compute the covariant derivative operator, the tilde one applied to this difference, minus the covariant derivative operator also applied to the difference. Okay, because eventually we want to try and get an expression for this guy. Okay, so we basically, and it's hard to get an expression for this guy. Well, we basically now have the difference of this guy, this operator applied to the difference of the two vector fields. Okay, and we simply work out the consequences. So you then apply the covariant derivative operator to this thing here. So I've just substituted in our expansion, and you apply the other one to that one. You know, due to the linearity property, you can take this thing and apply them to each element of the sum individually. You also know, due to the linearity property, that you can, sorry, not the linearity property, because these are actually functions. You have your Leibniz's rule that you can apply to the gradient of the functions. So the first step is linearity property, goes there. Okay. The next step is Leibniz's rule, but we can use this expression, which we used last time, and simplify it. Okay, so this is not a quick step. I haven't shown all the steps from here to here, but it was shown in the last lecture, where I actually derived, where you have the gradient of a rescaled covector minus the other gradient of the rescaled covector, and then you get this. So I've basically done that to get there. Okay, and then the amazing thing is, and this is why what the basis vectors you use doesn't really matter, except that they exist and the expansion is valid. Then if you evaluate this thing just at P, then this function kills the sum. Okay, because all these functions are assumed to be assumed to be 0 at P. So the results, this proposition 1, basically comes from the fact that this identity holds. Okay, in other words, if you're looking at the difference of the operators, the gradient aspect or the rescaling of the vector cancels out. That's it. And then you're just left with this. And then because you can expand the difference between two covectors in that way, these functions, once you scale it out, kills the term and you're left with it being equal to 0. Okay, so that basic, okay, so that's the reason. So we've proved this proposition 1, basically that this difference does not depends only on the value of omega at P. And that is exceedingly useful because we're now back to working with the tensor at the specific spot rather than worrying about how the field is being connected to each other. Okay, so there we go. And so it gives us another way to look at this difference between covariant derivative operators, even though we don't know them explicitly. And because it defines a linear map of omega in the covector space rather than dual vector fields in the neighborhood of P. Okay, so it's a change. It's like this, the difference part of the operator is entirely local. And that makes it nice. And why it makes it nice is because you can actually compute this. Okay, and so we're going to formalize that thing even further because this thing then becomes a tensor. Okay, and we just have to be careful how we choose to describe the tensor. And I could honestly say that this part of the thing I would not have been able to work out myself. Okay, well, it's just, you sort of, you know what you naturally would have, results you would have gotten to, and it's just not. That's something I use, and I greatly applaud Riemann and Christoffel and whoever did it. But it's kind of beautiful what comes next. Okay, so, okay, so this thing defines a linear map of omega and to a tensor of type, well, 0, 2. That's true for any derivative operator at P, right? It always increases the low index by 1. But it does more than that. And so because it applied to the one form defines that linear map, it also defines a tensor that looks like this. Okay? That you then contract to actually get, wait, let me go on. Okay, so it defines a tensor that looks like that. And the reason I say this is that given any two derivative operators, those two, the statement is there exists a tensor field that looks like this, such that you can express the difference between the two of them in the following way. Okay, so these two are acting on tensor fields, but their difference is exactly what we've said. It's a tensor acting at a specific point, and it maps it in that way. So you can write the difference like this. That's effectively what we did when we derived the difference between the two. Okay, and these things are nice. They are things you can compute at a specific point, if you can get them. I haven't yet said how you can get them, but they do exist. The fact that they exist is extremely powerful. And I'm going to show, it's basically the end of the lecture when we have the metric, I'm going to tell you how to compute it. And once we have them, we can do basically everything. So I think I'm going to give you another problem set. I might give you an example, and then I'm going to give you another problem set to sort of play with these things and to make them solid in your own head before I actually go on to looking at curvature. Okay, so we now have a way for a one form to define the difference between the operator working on it, two different derivative operators working on it, and we can encapsulate the entire difference in terms of this tensor, which has certain properties that we're going to now go on and derive. Okay, so the first one is, let us apply what we've just derived to a specific type of one form or covector that's the gradient of a function. So let WB equals to the gradient of f, okay, but we know that this is the special case where we actually have a handle on what the gradient does if we apply it to a scalar function. We know it's equals to omega b applied there. And then we can put this special case in there. Okay. And what we then get is that the gradient applied to WB is equals to the gradient applied to WB, but then I've used this expression to put it in there. Okay, and that's equals to C AB, the gradient of F. Okay, and what we know is that it's a tensor equation for both this gradient and that other gradient, and we know both of them are symmetrical. Okay, by our assumption, our what's it, commutativity assumption number 4. And so, so they're both symmetric in A and B, and therefore C, excuse me, must also be symmetric in A and B. Okay, so this is one of the properties of this tensor that we know exists, that we've defined, that we're actually now going to learn more and more and more about and eventually compute at the end of the lecture. Okay, so they're symmetrical, and we're now going to see what other properties they have. Okay, and it turns out, I'll give you the toekomstmuziek before I go on. It turns out the reason why this thing is so powerful, it's sort of like almost an innocuous argument. It didn't seem very complicated when we did it, but it turns out that you can actually use this quantity to explore the difference in action of the derivative operators on covector fields, so the up indexes, and all other tensors as a result. Okay, and that's what I'm going to derive now. And they're very cute derivations. The way of deriving it here is also actually useful because you can actually use it in other problems as well. So as I go along, I'll say a number of the tricks that I use or the things I watch for when I try and simplify tensor equations, and show you how the result comes. Okay, so the first thing we're going to do is we're going to look at vector fields, and then later we're also going to look at higher rank tensors, or rather I'm just going to sort of wave my hands and give you the results, because in a way it's obvious, but it becomes exceedingly tedious to write it all out. So the first one is, the first result, and this is just plain up, is that the difference of the derivative operator applied to a contravariant vector is just the same, the difference between the two, plus C, A, B, or C, B, A, C, T, C. Okay. And just be careful if you look at the indexes, right? The tensor equations, your indexes have to match. So here is bottom, top, bottom, top. Here, the summation is, it's the same B, top, bottom, A, that matches all the rest. And the contraction takes place from TC to a lower index of the of that tensor C. Here, when we apply the difference, just look at the difference, because it's something to remember. It stops you from making mistakes when you calculate. Here at the bottom, you have AB, so they match. Here you have C, it's contracted with a top index, AB. So the thing is symmetrized over only the second two indexes. Remember that we derived over there. And times omega C, and here's a minus sign. So look at the difference. Here you're actually contracting with one of the indexes that are symmetrized, and then you have CA there. Okay, so there's a difference between the two, and it's another reason why your vectors, your contravariant vectors and your covariant vectors are different. If you apply the derivative operators to them, the differences are different. Okay. This result I just gave, let's just derive it, because it's quite a cute way of deriving it. So the proof is basically compute the difference in derivative operators applied to this contraction. Okay, and we're going to compute it two ways. The first way is we first compute the contraction. So we have that omega b t b is just a scalar function, okay, because you've applied the contravariant or the covector map to your actual element of your vector space, and then you get a scalar function. You know, it's a function of f effectively on the manifold, and by 4, our assumption that's associated that with the covariant, or sorry, the derivative operator with a directional derivative, we have that the two operations agree. Okay, so just doing the contraction first, we have that thing has got to be 0. Okay? But now if we delay doing the contraction and we first apply the operator and we use Leibniz's rule to apply the operator, what we get is this thing. Okay, so there we derive, it's basically just using the definition, we're applying the difference in operators to the first element to omega b, multiplied by TB, but then we've got to add the second one where we have omega b out, and then we apply the derivative in operators to TB. Okay, so that's just the Leibniz's rule expanded. Then, what we then do is we already know through our very, very careful discussion of CAB and the fact that it only depends at a point, which basically reflects that you're actually rotating your coordinate, your underlying vectors. We know that that applies, that we know that this thing is already defined for us, and it's defined over here. Okay, so we can basically go and we can replace this expression with that careful argumentation, and we can then look at the second expression, and for now we just leave it. Okay, because it's actually the thing that we want to derive. Okay, so what we're going to do now is we're going to just regroup the thing. Okay. Okay. The next thing we want to do is rename contracting indexes. So this is another trick that's exceedingly useful when you do tensor calculations, because these indexes don't have a specific value, they basically stand for something. So whether you sum, it's basically changing the name of your summation index. But if you do that, you can often simplify an equation much more. Yeah, you just simplify the equation because you make the terms look like each other and then they just cancel each other out. So here, if you rename, the reason why we want to rename it is because we want to get this omega b out of the picture, because the thing we're deriving is basically doesn't depend on it. So if you rename C to B and B to C, okay, then you basically get C B A C omega B T C. Okay, it's still entirely valid because the only, in some sense, free index is A. Okay, so this thing is actually describing a covariant vector. That's what it totally is. So if we do that, we get that term is equals to that term. My question to you is, are you comfortable with that? If not, get comfortable, but you're allowed to do this. It's a trick and you'll use it again. You must probably get practice in using it at some point. But all you've done is basically renamed the label of the box that you're going to sum over. And I've just chosen to relabel it so that I can do more things with manipulation. Okay, so you relabel the index, you get this tensor notation. You can then factor omega b out. Okay, and you can reorder it a little bit. And so all I've done is omega b, I've taken it out there, omega b, I've taken it out there, and I'm left with this expression. Okay, so I still have just A as the free index. I mean, okay, so an index I don't contract on in the expression. Those tend to be fixed. Don't change those. But anything that you're contracting on, you can just relabel anything random. Okay, so you could have changed C to D and nobody would say anything. And you could change B, as long as you change it in the whole expression now because you're contracting outside the bracket, you can change it to something else as well. Okay, so now the argument goes, this whole discussion has been true for any element of your tangent space and any element of your dual space. Okay, in particular, and we know it's got to be equals to 0. Okay, and it definitely has to be true for non-zero omega b. Okay, so we've got to have that this bracket vanishes. So it holds for all one-form cotangent fields omega, and so we have basically derived the result up at the top. Okay, so we now have a difference in the expressions for the covariant, for the derivative applied to the difference between two derivatives applied to a vector field, or contravariant vector field. Okay, so the result follows. Okay, and then once again, this is just notes, because we're going to use the structure repeatedly later on. We're going to eventually add meaning to these C's, but this formula, and actually add a specific meaning to that one, but this formula is going to remain the same, and this sign difference, don't make mistakes, there's unnecessary mistakes. Okay, so the same approach that we did to define, we now define it for an element of the dual space and the vector space, and you can go on and do the same thing and say define the difference of the two derivative operators applied to a, say, type 0,2 tensor, once again by computing its impact on that tensor contracted with 1, 0, like a vector. Okay, and then you go through the same thing, and what you get is sort of by induction you can build up a general expression. Okay, and the general expression you're going to get, I'm just going to give it to you and then show you in some sense how easy it is. Okay, so the two difference operators is, okay, so this is an equation that I'm going, or this is basically the main result is the difference between two derivatives operators is completely characterized by this tensor field C, and the proof of that thing is basically you want to get a general expression for the difference between the operators applied to a general tensor. Okay, and what you do is, just as I've described, you apply it repeatedly to higher and higher order tensors, and then basically inductively show that if you have a tensor of that type, the difference between two operators applied to it is simply that equals to that plus two additional terms. Okay, or rather not two additional terms, plus k plus l additional terms. Okay, so the first basically k additional terms is you take a sum over each slot in your tensor, so each covariant slot in your tensor, okay, so the parts that behave like a vector, you multiply that particular slot by what we found for the vector transformation. Okay, so what you do is you choose your slot, indicate the slot that you're summing over, you put an F there, you contract it with that C tensor, with the F below there, C, and then you replace the index of the slot in the top of your CI tensor. Okay, and the bottom remains the same, so that basically accounts, in a way of thinking about it, for all the rotations that are taking place for your covariant components. Okay, and note that this is a sum over, so it's basically got the k slots in there. And I'll give you an example in one of the later proofs. And then you've got to subtract, so you use the the difference rule that we originally derived when you're working with cotangent vectors. You've got to subtract the C, where the F now identifies each slot in the lower indexes. Okay. And you replace the slot that you are contracting with the index here, CBI. Okay, so the tensor equation is entirely valid, it's just written this way. So the difference between the two derivative operators is basically the ordinary difference plus these things, these tensors that depend just at the point. And the converse is also true. You can also show that if you have a valid derivative operator, and C is an arbitrary smooth tensor field, okay, then if you construct this beast, you've constructed another valid derivative operator. Okay, and that's necessary. You need both the one and the other one for saying that it's completely, the difference is completely characterized by the tensor field. Okay, and it's true for its operations on every single tensor, okay, which is kind of nice. So this thing is a 3-index thing, which is awkward, but it encompasses basically all the rotations that are taking place, in other words, for these potential equations to hold, which is kind of nice. Okay, so all you need is a index with the lower index that's a C that is symmetric in the lower indexes, and then if you define the derivative operator like the above, you make that the definition, you can show that it's a derivative operator. Okay, so you've gone both ways, and that's it. So the only thing is that there's a large freedom. If you've said nothing, and this is what we're going to change towards the end of the lecture, if you said nothing about your derivative operator, the difference between two, sort of, in some sense, C encompasses the class of all possible derivative operators, right? Because you just define the difference between them. And just to see, in some sense, how large the possibilities are, you have, just count the components possible in C. So it's basically n times for the top index times n each for the bottom ones. Well, definitely n for the first one, and then because it's symmetric, you lose all the lower diagonal, the components below the diagonal. That's why it's plus 1 divided by 2. Okay, and you can just check, like for n equals 4 index tensor, it's 40. For n equals 3, it is basically 9 times 18. Okay, so there is a lot of indexes that you can work out, and you'll be working them out, but there's a systematic way of working them out. Okay, so once you have that, you've basically defined you can take derivatives of tensors on that manifold very, very well. Okay, so now comes to the slowly actually getting to compute them. I just want to see how fast I'm going. And there it introduces the idea of a Christoffel symbol. So what we're now going to do is we're going to look at the case of, we've got one derivative operator we know is easy to define, and that's just the coordinate derivative. Okay, so we're going to basically say, let us choose this omega tilde as the coordinate derivative operator. And then we know that all other derivative operators are related to the coordinate derivative operator if we've specified the C. Okay? And that's where the Christoffel symbol comes in. It's just a way of specifically identifying the C's that are associated if you've actually chosen to define a coordinate derivative operator to start your calculation from. Okay, so in the case where omega tilde is just dA, which we defined in the last lecture, where you basically define it as a thing that you get by choosing a basis and then computing all the derivatives of all the components on that basis, and then you can transform it using the tensor transformation laws to anything else. Okay, so choose a particular coordinate basis, choose a particular dA associated with that coordinate basis. Then for that case, we have that C is simply, we call it gamma AB, because I think they originally they first viewed the thing just as the coordinate basis and then generalized the theory. Okay, so if you have chosen the derivative operator to be just the ordinary partial derivatives, you have this expression. Okay. And this thing is called the Christoffel symbol. I know nothing about Christoffel actually, but I'd like to. So now here's the thing. Okay. So recall that the way we defined a particular dA is we actually chose a coordinate system or a chart. And then we said that that's fine if, in addition to choosing the chart, you know what these gammas are on that coordinate system, then you've actually defined the derivative operator. Okay. But if you change coordinates, and this is the important thing, If you change coordinates, you get a new derivative operator. Okay. And if you change coordinates, the only derivative operator changes to a new one. Okay, the two cannot be transformed each other because it's basically that the partials. If you take this guy, this operator, and you transform it into a new thing, the thing you obtain is not the partial derivatives on the new basis, it's something different. So this is just what I'm saying, that if you change coordinates, the only derivative operator that you define in the old coordinate system is not comparable to the new one. You have a new coordinate things, and you also have a new tensor gamma, a gamma prime. So where this is important is, and this new gamma prime is not related to the old one by tensor transformation law, because the new operator x delta like that is not related to the old one because of the tensor transformation law. And that's very, very important. In fact, you would have a lot of textbooks that will actually tell you that gamma, the crystal full symbols, are not a tensor. Okay, which sort of is contradictory because I've just said that the tensor field C exists. But the reason why they say that is that never, ever, ever, when you work with gammas, do you ever apply a tensor transformation law to them. Okay, because always when you've gone to a new coordinate, you want the new gammas associated with a new coordinate system. So what I'm trying to say here, if you start multiplying things with like the x dx gammas with that, you're making a mistake. Just stop. There's like 40 indexes of work that you're going to do unnecessarily. Stop. Okay. But it also explains that if you read a textbook and somebody tells you that full symbols are not a tensor, what they're actually meaning is that if it's the combination of both the derivative operator on a particular coordinate basis and gamma on that coordinate basis that combine to actually define the operator. Okay, but when you go to the new basis, you get a new derivative operator and a new set of gammas, and the way to compute them, and you cannot transform the one into the other with just ordinary coordinate transformation. So you basically have two parts that don't transform themselves like tensors effectively, that combine to make something that transforms itself like a tensor. Okay, so lesson of this bread thing is, do not ever try and brute force transform a gamma from one coordinate system to another one. You're going to make a mistake. What you are going to do, and I'll show you how to compute the gammas, is when you have a metric, you compute the gammas directly from the metric using partial derivatives, which you know. But this is coming. I'll simply derive how you do that. Okay, so parallel transport. So this is just formalizing what we actually discussed in the last lecture. Okay, so now that we've specified our derivative operator and the difference between two potential derivative operators, and we said all that stuff is kept in the C's, we can define parallel transport. So remember, it was given a derivative operator and a curve with a tangent t. The vector v at each point to the curve is said to be parallel transported along C if its covariant derivative vanishes along C. And this is just how you express that. Okay. So you apply the covariant derivative operator to the vector, and then you contract it with a tangent to the vector. Okay. And so this is the abstract index notation way, and I'm just going to give the other way, just sort of rewrite it in the different ways that you actually have, and that when you see these things in the textbook, I don't know exactly what Nigel Frost is using, but it's not new. So this is basically the requirement asterisk index notation. If you express it in terms of a derivative operator on a particular coordinate system, what it's going to do, it's going to look like that. You're simply going to have TC times the derivative operator, coordinate derivative operator applied to B, plus Okay, and this comes directly from how that law that we derived from the previous slides, plus TC times, okay, because it is a contravariant vector, times the gamma, because you're working in a specific coordinate system, times B CA VA. Okay, oh, no. Okay, if you go on, another way of expressing it that people also do is that if you now, so this is abstract index notation, assuming you have a derivative operator derived given on some coordinate system. If you then go and you express it on a coordinate basis, in other words, this thing just becomes the basis components, and you say parameter t is that parameter that actually identifies the points along your curve, then you can also express it this way. Okay, because you then have this t identified that way is simply ddt of the vector component itself along the curve. Okay, because this ddt you can expand effectively using the chain rule as partial dv dx, or the coordinates, so it's effectively that thing multiplied by the tangent vector for that particular coordinate times dc. So this guy and that guy, if you're working on a coordinate basis, are equivalent, and then you just have this thing. Okay, so here you can start seeing how the gammas start keeping track of how your vectors are shifting. Okay, that's a definition for parallel transport of a vector, and we're also going to practice with that. And then parallel transport for a tensor is simply the same thing. It's simply the coordinate derivative operator applied to your tensor contracted with the tangent vector of the curve. And that's also going to be equal to 0. Okay, so that's just a formal definition of parallel transport. If you want to write down equations, and we will. The parallel transport of a vector VA also depends only on the vectors, the values of the vectors on the curve itself. Okay, because you have hit it, you make that contraction. So when you actually express it on a coordinate basis like this, right, you know what the gammas are along the curve. You start with an initial vector, and then you know how the actual components are changing because you have a differential equation that you can write down. Right, because these are functions of the points on the curve. The tangent vector is also functions of the point of the curve. The v is unknown, okay, because it's a differential equation. But you've defined a differential equation for it, which is a first order system, which you are guaranteed by the theorem for differential equations that it has a unique solution. So you're fine. Okay, so you basically can worry just about the vector along the curve and not the vector field. You can also say that there's a unique solution of v. So you start with a specific v, and then you know how you have this. You solve this equation, which is not always easy, for how the components change, but you know there's a unique solution. Okay, and it's this very thing that you can start at a point P, define a curve to another point, and then use basically this formula or that formula and change the vector to a unique vector at that other point. And that gives you a way of actually starting to identify the tangent spaces between two points, because you simply take your basis vectors of your one tangent space, you parallel transport them along the curve till you get to the new point, and then you see the relationships between the basis vectors at the new point and those from the old one that you've parallel transported, and you can then actually connect the two vector spaces. Okay, so there's a unique solution, and that's just what I've been saying. Okay, so VA at P uniquely identifies with VA all the way along the curve, and parallel transport can be used to identify the tangent spaces at 2 points, VP and VQ, if you're given a derivative operator, and a curve connector. Okay. And I'm not going to go, there's a whole theory about this that people have actually expanded if you don't have a metric. I'm not going to do that. I'm going to go for metric because the nice examples are there and we can start computing things more than doing the abstract things. Okay, but I just want to give it to you unless, in case you come across it in, if ever you want to read your own stuff. It's called a connection, which is an obvious word, but a lot of people will talk about connection. If you go to a conference and you hear people talking about the connection, what they are basically meaning is a mathematical structure arising from a curve-dependent identification of tangent spaces, right? So a particular, if they are working with a manifold where they don't yet know the metric, then they use the connection before they've known the metric at different points. And there's more theory there, but I'm not going to go there. I'm just saying you that this is the big word they use. So given only a manifold, you have many distinct derivative operators. You can still do a lot of them, and you go down this rabbit hole. They're possible. In fact, we counted how many different operators are possible. There is n squared times n plus 1 over 2 of them, and none is naturally preferred over the others. Okay. However, if you're given a metric, this changes, and you get a unique one. And that's what we're going to look at the rest of the part, and we're now going to slowly get more and more practical and computing things and actually see the power of this giant machine that we've been deriving for the last 7 weeks. And so, yeah, and then we're going to do the cool stuff like looking at the geodesics and things. Okay, so the metric, so well done for sticking with it for 7 weeks, but now we start really computing stuff. So the metric changes this and it picks one. Okay. So, and I just want to show you how it picks one. And then I'm going to stop, and then I'll give you sort of examples to do to actually try and calculate the thing. So the reason the metric picks one is because a metric gives a very, very natural condition that is a sort of a logical requirement if you move a vector from one place to another one. Okay, and the requirement is that the contraction, say with a tangent or the inner product mustn't change, obviously. If you have two vectors and you move them to a new place, then you want their inner product to remain the same. It's a very natural identification. That's what we get with the metric, because the metric immediately gives the map between the covector and the vector space, or the dual vector and the vector space. Okay, so the metric gives a natural condition to impose on parallel transport to choose a particular derivative operator. And the way the natural condition works is, given two vectors, okay, their inner product, which is just defined if you have a metric, should remain unchanged if we parallel transport them. Okay, so that is the requirement that actually makes you choose a particular derivative operator. Very nice and clean, and also very powerful because it actually tells you how to compute the things. Okay. So what we're basically going to require is our parallel transport of the inner product has got to be 0. So we're parallel transporting a scalar field, because this is effectively a function on your manifold. And we require that to be 0, and what we now do is simply work out the consequences and manipulate the indexes, and we get all the nice cool results which we can then use, and you can like memorize and keep it for calculational purposes, and also for seeing fascinating things about manifolds. It actually gets you a tangible thing. So in fact, I mean, if you want a physical example of parallel transport that we see, that actually has been observed in strongly curved spaces, a pulsar is like this thing the mass the size of the sun that's been squashed into 10 kilometers. So it's very, very dense. It's like squashing the Earth into a cup. Okay, it's the same density you'd achieve. And so what happens when a star collapses like that, you have a big star that's possibly spinning slowly, and then when it collapses, it goes zzz up just like the ballerina does. And something like that is basically a vector that's pointing in a certain direction because it's spinning around. It's just like a bike wheel. You change it with the inertia change is very difficult. It takes a lot of effort to change it. A similar thing, if you have a pulsar and it's spinning, it doesn't want to change. So it gives you a very, very natural idea of a vector. Now, if you were to have a pulsar or this object just moving without another gravitational field, it would just remain. It would just keep its angle. In classical physics, it should also keep its angle. Classical, if you were just putting it like following Newton's laws. What happens, however, if you put it in a gravitational field that's non-uniform, then the thing actually changes without giving off radiation. Okay, so, and we can actually see that, and we can compute it using that equation. And the way we see it, the most beautiful example is if you have two pulsars going around each other, okay, so then the one that has an axis like this has sort of will move around the other one, feel its field, and it will be parallel transported. Okay, and the other one will also. Okay, now if you solve those equations carefully, you'll find that if the beam is in the plane of the orbit, it's not going to move. It actually is going to stay the same. But if the beam or the vector is at some angle to the orbit, you parallel transport it and you take it once around the orbit and you've actually changed it a little bit. Okay? And they've seen this. Okay? So there is a pulsar system where the one beam lies in the plane of the orbit, and you can see that because it was, somebody said, like, nature provided the perfect system. You know that because you can see the one pulsar eclipse the other one. So we just happen to know that we are looking at the pulsar system like this, flat. Like, for example, on my desk, the pulsars are lying on the desk, and Earth is sitting here. So we're actually seeing them. So what happens is, and the reason we know that, is the pulsars are very, very small. So if you have one that has a beam, and it's in the plane, then actually two things are going to happen. One, when the two pulsars are lined up together, you won't see the beam. Okay? So you'll effectively have an eclipse. And then when you go past, you'll start seeing it. So that's the evidence that both the pulsars are lined up and that the beam is in the plane. Okay? So that is, so that we know. But that beam in the plane is not the one that rotates. The one that rotates is the one at an angle. And we happen to see that beam as well. Okay? Because there's nothing, because it's not like a laser, it's like got a thing. And as time goes on, and this is years, they've watched it for years, they've actually seen the profile of the beam changes. So you actually see the beam move away from us and towards us, and it's actually disappeared at the moment with the predicted speed. What we know exactly, it's a beautiful check, and we actually expect it to come back at some point. Okay, so that's one of the tests where we've actually seen this happen in wonderful form. Another experiment that they did is they shot up a satellite with balls that they spun up very, very fast and let it rotate around the Earth for thousands and thousands of times, and tried to measure how these balls changed their thing. They didn't measure it very, very accurately. There was problems with the whole experiment, so it wasn't as an accurate confirmation as this pulsar thing is, but they've actually seen it. So when you think of parallel transporting, the natural way is to think if you have this little vector, which can be a spinning ball, if you move it around, it's going to come back and it's not going to be exactly the same as it was later on. Anyway, okay, so back here. So to identify parallel transport with the metric, we're going to go through the mechanics of requiring that this inner product remains unchanged. Okay, and we effectively are parallel transporting a scalar. Okay, so the expression is basically, we require this thing to hold true if we have parallel transported both vectors. In other words, if TA, derivative operator applied to VB is equals to 0, and TA derivative operator applied to omega B is equals to 0. And then what we do is simply use Leibniz's rule and expand out this entire beast. Okay? And impose the requirements. So if we expand out the entire beast, we get that this thing is equals to the operator applied to the metric times VBWC plus the metric times the derivative operator applied to VB. Okay, and I've just moved TC and I can. Plus the metric times the derivative operator applied to the final one. Okay, so it's just repeatedly applying Leibniz's rule. And now you can use the fact that we're parallel transporting the vectors. So this dude goes out at 0, and that guy, this guy goes out at 0. Okay, and you're simply left with this expression. Okay, and we want to set that equals to 0. But we have made the argument for any vector, we wanted to hold true for all vector fields and all curves, so all TA. And so the only way that that can work is if this thing is 0. Okay, so it must hold for all curves C and vectors, so we have this condition. And it is this condition that actually allows you to uniquely identify a particular derivative operator, and the proof of that actually gives you a way of computing the C's. Okay, so this thing provides an additional condition which we can then use or impose on our different derivative operator to choose a connection, and it turns out that that's a unique choice. There's only one. Given a metric, there's only one, and that's the theorem we prove next. And that only one we can also compute directly if we're given the metric. And then that only one is effectively this intuitive picture that I've been giving you of what the C's are, is sort of like fixing the basis vectors, that it's a covariant thing that you've defined. That's what it is, exactly. So the way the proof goes is let GAB be a metric. Then the theorem is there exists a unique derivative operator, nabla A, such that it satisfies this thing. Okay, and the proof also starts giving you once again ways of how to compute with these things. So the proof goes, let this thing be any derivative operator. Okay. So we start with any derivative operator, so we know it exists, and then we fix it so that this property holds. Okay, so remember we have the class of all possible derivative operators. We know their difference is characterized by those C's, which is a 3-index tensor. If we can uniquely get those C's, then we're done. Okay, and that's what we're going to do. And it's kind of a very cute proof. And so, just an example. So let this thing be any derivative operator, and for example, you could use the ordinary derivative operator to start. And in fact, that's what we're actually going to do in a while, but not now. For now, we just say any derivative operator because all you need for the proof, and this is one way of choosing it. And so the aim in the proof is simply to say, find all the C's, because then you basically have the class of all possible derivative operators, and then choose them such that this condition holds. Okay, and you'll find that that choice is unique. If you can show that that choice is unique, you've proved the theorem, and it is. And so how it goes is, so we choose the C's such that the derivative operator determined by that guy and the C's obey the required property. And then we are going to go additionally, and that's going to be simply obvious, show that the C's are unique. Okay, the C's have a unique solution. And it turns out that we find an algebraic ways of defining the C's, therefore they must be unique. Okay. Okay, so what we have for the general equation that we have for the difference between this operator and that one applied to a tensor. Okay. You know, that big one that I said I'd give you an example. Well, this is the example that's now coming. Okay, so for this operator applied to a tensor, what you basically get is we simply want to expand it in terms of the operator we already know. So we want the new operator, which we want to prove is unique. We want it to have this property, okay, and we can express this property in terms of the operator we know that it exists. Okay, so we express this property using that difference rule that we had in the beginning. Okay, so we have, and this is where both indexes are lower, so you're working with minus signs, and only one minus sign is actually necessary. I got a bit excited. So you're working with minus signs, and then look what I do. So the one is the derivative operator applied to C, which could just be the partial derivative. Sorry, applied to the metric, minus the C times, you replace one of the indexes in the tensor with the top, and then you take the index you've replaced, which is the B, and you put it in the Christoffel symbol. Okay, and then you do it for both lower indexes. So minus the second index. So you have D over there. Now that you replaced. Now you replace. You replace the B, and now you replace the C. Okay, and that's what that sum meant. You basically have to add a C times the tensor where you've replaced each of these indexes in turn by the D. Okay. So for a two-index tensor, you always have two elements, or however many covariant indexes you have. Okay, so then we get this expression. Okay, we know this thing is 0, and what I've done is I've simply view this thing, then now I'm viewing it as a tensor that I can contract down. So I've simply viewed this G DC as a way of lowering this index, which I'm entirely allowed to do. Okay, and I've lowered this one as well, which I'm entirely allowed to do. So then I get this equation. It's basically C cab is plus C back is equals to this, where this derivative operator is known. Okay, so now the cute thing goes, and this is an index game, which for other proofs it's also, you play similar games, and this is what I think you'll be really good at actually. So now we can go and we can say, fine, we have this expression, but these things are just labels, so I can change the labels. So this expression is entirely equivalent to saying it like that. Okay, I'm allowed to do that. It's just a tensor expression. The index, the labels themselves contain no content, they just stand for the places. So here I've effectively simply switched A and B around. Yeah, A and B switched there, A and B switched there. So these two things are entirely equivalent, it's just reclaimed indexes, and I could play it again. Okay, so here I've switched almost all. I've basically taken this, the top one, and switched a B and C around. Okay, so I got this one and there, I've switched B and C, and there I've switched B and C. Okay, so I now have three expressions. And the nice trick is, I want to find a unique way of defining the CABs. And I can do that if I can get rid of, I've got 6 of them there. if I can get to the point where I have CAB equals to something in terms of the metric, and these things are potentially just derivatives of the metric, then I'm done. And it's an algebraic expression, so it's unique. And the cool thing is, I can do that. And the way I can do it is, suppose I add these two things, and I subtract the bottom one, And I make use of the fact that I know these two indexes are the same. So that's the important fact. I know that the symmetry property in the last two indexes of my C holds. Okay, so what I'm going to do is I'm going to add 1 to 2 and subtract 3, and I'm going to use this thing that DEF is equals to DFE. Okay, if I do that, then I get this expression. Ah, beautiful. And that expression is immensely useful. Okay, it does several things. But let's just check that it's right. Okay, so this right hand side is simply 1 plus 2 minus 3. This left hand side is this one plus this one is, and you can switch them. So these two add together to get 2CAB. Okay, so those two stay. Then I'm subtracting this thing at the bottom. This guy is equals to that guy, so it kills that guy. This guy is equals to this guy, so it kills this guy, so we're fine. So we actually have derived it. And then what I do is I use the upper metric to raise the index again. And I divide by 2 and I get this expression. And this is a very important one. This is, I don't advise people memorize many things, but do memorize this one. And you'll see it has a logic that goes to it. But it simply, whenever you're given the metric, you can then use it to compute these C's. Okay. And if so, given any derivative operator and given a metric, you could now construct the C's uniquely that will give you another operator that will satisfy this. Okay, and it is unique because it's just an algebraic construction and we're done. Okay, but more powerfully, we actually have a computational tool, which is this thing. Okay, and I'm almost done for the lecture as well. And this thing, I didn't even write this down. The C's associated with the metric constructed in this way is called the metric connection. Okay, so remember I said the study of connecting vector fields at one point to another one using this idea of a derivative operator, or the difference between derivative operators and parallel transport, is basically defining that mathematical structure as a connection. The specific case where you're given a metric is a metric connection, which most people, which is the only one we'll look at, and most of the work is done there. Okay, general relativity just uses a metric connection, and so end of proof. Okay, so the metric determines a unique derivative operator, and they often call it the natural derivative operator given a metric. So usually, if you're given a metric, you can assume whenever they use a derivative operator, it's the one associated with the metric. There are very few articles that actually do anything else, and it's usually very intense mathematicians that are exploring certain things. Careful, you can have more than one metric on a manifold. In that case, you're going to have to have your operator. You're going to have something that identifies the metric and something that identifies the operator. Now, if you're given the components of a metric or a basis for the metric, then because the computed C's were only dependent on the derivative operator you originally defined applied to the metric in a specific basis, you can immediately compute them. Okay, so given a metric and given a derivative operator, and this is just the ordinary coordinate derivative operator that can be applied to the components, then you can compute the gammas. Okay, and this is the method you always use to compute the gammas. Never, ever, ever, ever try and transform one gamma from one coordinate system to another one. Always use this method. So if you think of gamma, think this thing, okay, which you will keep very safely in your head somewhere. Okay, so we can compute the gammas given the components of G, A, B by taking partial derivatives of the coordinate basis components. Okay, so we're entirely back into the realm of taking derivatives in the way that we know. Oh, that killed it. Anyway, so we're entirely back in the realm of, I didn't get the last, somehow it went missing. So we're entirely back in the realm of simply computing directly. Okay, and so what you would do, and that's actually the example I wanted to put up, but I didn't get to actually work it or sort of type it out, is remember that transformation I did, the transformation example I did in the previous case, or in a few lectures back with a metric, where I showed you how the actual vectors rotated. I'll give you the gammas for that one, so that you can just work it through yourself and check that you're actually applying the rules correctly. And then I'll give you another metric to work out the gammas for, just so that you can get some practice and get a feel for it. And then I'll give you an example of parallel transporting a vector. Just a simple one that you can actually see how it works. Because now we can actually compute. Because now you can compute your gammas given G, and then you can work out your parallel transport equations. And you can see, like, just maybe even I must still work it out, but maybe it'll just be like taking a vector around the big circles on the sphere, just so that you can see how it actually works out. And you can actually compute exactly that mismatch. One of the research problems that I still actually have is trying to find clever ways to actually do that mismatch problems for the GR. Sort of also exactly the calculation that the pulsar people, that you do for the pulsar, is simply to do it nicely for the GR and see what can be there. So, I mean, those are like toy problems. You can now physically do so much with these, with the metric. The moment you have your gammas, because you then can define this derivative operator, which you've actually defined a derivative not only of a vector, but of all tensors. And it is contravariant in the sense that it's unambiguous as you go from coordinate system to coordinate system, provided you are working your gammas out in this way. Okay, and yeah, as we go on, you'll see the power of simply doing that, where you can write down equations and then know that if you wanted to express in a certain coordinate system, if you're given these gammas, you've already got the derivative out. So the cool stuff starts now. Sort of the computationally cool stuff starts now. And yeah, I'll start. What I'll do the next time is I'll give you the example that you know how to do it. The next time I'll look at curvature, which actually is effectively keeping track of how the vectors change. And after that, it'll just be specific examples. And I'll do the GR example and maybe some other interesting geometric examples. So, questions?